Good. Okay. All right. So as we're looking at Canvas, we have the review questions, homework, and upload. And so if I click this particular guy, it opens up here and it says, yes, you do have for the week some review questions that you need to look at, and then upload your answers. So if I open this particular guy and we look at it, open up Microsoft Word. Okay, and let's see, enable editing. All right, and let me change the share so we can see this particular document. And now we want to look at this document. Cool. Okay, so for this particular exercise, a couple of things here. Question number 2 has data for current, has data for voltage, and you're supposed to plot things in this graph. Now they're using voltage on the vertical axis, they're using current on the horizontal axis. I'm going to do something slightly different in the example that I'm going to be talking about. So although many of you, excuse me, who have submitted this answered a lot of questions, some of the questions, actually nobody filled in this graph. So you want to look at this very closely because it does affect your grade. And it's an easy concept to understand how voltage and current are related relative to this graph. So let me go ahead and do this with you. Let me stop this share and let me go to the camera, IPV, okay. And let's make sure I have this in good focus. Move this out of the way. Move this guy out of the way. And this is in good focus. Yeah, pull out your calculators if you would, please. We'll have a pretty simple circuit for us to play with. Graph things pretty easily. All right, so the circuit will look like this. We will go. It'll still work out, but this is more to the specifics of your exercise. Make this guy here, make this guy 10 ohms, and make this guy go 1 to 10 volts. How about that? All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 volts. And we're looking for I, a column of I in the middle, and we have R of 10 ohms. Okay, so what will be my, I'm going to do this a little easier and make these numbers, that way we won't have any millis, okay? So 10 volts, what's 10 volts divided by 10 ohms, everybody? 1 amp, yes? What's 20 volts divided by 10 ohms? 2 amps, yes? What's 30 divided by 10 ohms? 3 amps. You see a pattern here? What's 40 divided by 10 ohms? 4 amps. What's 50 divided by 10 ohms? 5 amps. 60 divided by 10 ohms will be 6 amps. 70 divided by 10 ohms is 7 amps. 80 divided by 10 ohms is 8 amps. 90 divided by 10 ohms is 9 amps. And 100 divided by 10 ohms is 10 amps. Is that pretty straightforward math there? Nothing complicated about that so far. So what happens graphically is this. What they're asking you to do is they give you these voltage and they give you these currents. And so we're going to have a graph like here, and we will have, okay. So 50 volts, 100 volts. Okay, here. Oh, thank you. All right, 10 volts, 20 volts, 30 volts, 40 volts. So here would be 60, here would be 70, here would be 80, here would be 90. So there's my voltage. And I'm going to put current on this side. And current ranges from 1 to 10 amps. Okay, so we will go here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8, 9, 10. I'm using a reverse scale, but the end result is the same. I'm not doing your exercise for you, but I'm showing you an example of how this should work out if you are doing this and plotting things along. So from our data, which is over here, look at the data and look at the graph that we're going to plot. Let's see what we've got, okay? So at 10 volts, we have how much current? 1 amp. So here's 10 volts, here's 1 amp. That puts the intersection right there. At 20 volts, at 2 amps, here's the 20 volts right here. There's 20 volts. Here's 2 amps. Where do they meet? They meet right here. Where does 30 volts and 3 amps meet? Well, 30 volts is right here, and 3 amps is right there. And then 40 at 4, it'll be something like this right here. You're starting to see a pattern. 50 volts at 5 amps. I'll draw this guy up. Draw this guy over here. 50 volts at 5 amps. 60. Shoot this guy up at 6. So what do you see here, without plotting them all out, do you see what is called pretty much a linear relationship that occurs between voltage and current when resistance is constant. Okay, we held the ohms to be 10 ohms in this schematic. That was fixed. The only thing that was variable was the voltage. So a variable, just simply draw a diagonal across any component, and now it's a variable component. And how did we vary the voltage? We varied the voltage from 10 volts up to 100 volts. Here's our 10 volts to 100 volts. We fixed our ohms at 10 ohms, and we calculated the currents. So all of these were calculations. And we plotted voltage versus current, and it shows what type of relationship you want to conclude from here. This is a linear relationship. And so that's what you ought to be doing when you are looking at this exercise. When you are looking at, okay, that looks good. All right, when you're looking at this exercise, so let me change the share to back to here. You happen to have voltage on the vertical scale and current on the horizontal scale, so you're supposed to take this information based on this and plot it in here and see, do you achieve a linear relationship as well? I believe you do. You just need to put them in. And so how do you submit this as a homework assignment? A couple of different ways. You could print it out, and then you could draw them in and then take a picture of it and upload it. Or you can also import this into PowerPoint, let's say just this particular part. Let me show you how to do that. If we just take this particular part and take a snip of this, so take a snip. So I'm going to come up here and do new snip, and I'm going to take just, my mouse is here, I'm going to take this particular part of it. Now I'm going to take this and copy this and then go to something like PowerPoint. Opening up PowerPoint, blank presentation, and I'm going to switch screens in a moment so you can see the PowerPoint. All right, so let me go ahead and change the share so you can see the PowerPoint. So share. And I'll just share this screen and select. All right, so here I have a blank PowerPoint page, and I'm going to paste this guy in here. So now I've got the graph in here, very nice graph. And if I were to plot the information in, all I have to do is hit Insert, Design, Insert, Draw, Insert Shape. Insert Shape. What do I want? I want a little dot. So here, a little circle. All right, and then so it may turn out there's a little dot, and I can grab it right here and put it wherever I want. Duplicate this, put this wherever I want, or wherever it calculates to be. I don't know. I mean, this one might calculate differently. This one might go to here. This one might go to here. This next one, duplicate, might go to here. If that works out to be the case, then I would insert a line. So come in here, shape. Let's go ahead and draw one from here and straight out with an arrow. And I might want a different color on that. So go ahead here, pick red, let's say, and I want to make this more prominent. Weight, boom. So now that's one way of doing this. If the points plot differently, so for example, if I come deselect and come over to here, trying to hit that point. Let me move this guy out of the way because I want one of these guys. Okay, move this here. All right, so move this guy back. So let's say it plots a little differently. Let's say this particular guy ends up plotting here. And then duplicate. And the next one is here. And duplicate. Next one's about there. Duplicate. Next one's about there. Duplicate. Next one's about there. Then I go to draw a different line. It might look like this. Insert. Shape. Pick the arrow again. Start from 0, 0, come out this way, and home, shape outline here, and then the weight, make it a little thicker, boom. It might look like that. So you can do this in software. If you choose, if it does work out to be a linear relationship, you'll have to do your own points and plots and see how it works out and upload that work in with your homework. So anything that you have submitted so far where you did not achieve maximum points, you have till this next this Sunday night to fix things if you choose. Okay? Any questions about how to deal with this particular graph and how to plot points and things of that sort? Any questions at all? Brad is smiling. He's got somebody chatting with him in the background. That's okay. Yay, family members. You got to love them. All right. Let me go ahead and minimize this guy. And we're done looking at the snip. We don't need to change this, save this on the snip. Now, there was another question here. Question number 10 was really interesting. Question number 10, some people who did submit had a had this. They were doing a calculation on number 10, and on number 10, you see that fairly clearly. Let me magnify that question so you can see it a little better. Here, 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 here. Okay, is this is now big enough for you to read? Okay, so it says, what would happen if a wire having how much resistance? No resistance, 0 ohms, were connected directly across the terminals of a 6-volt battery? How much current would result? Well, you're going to use Ohm's law, and Ohm's law says, okay, I want to calculate current, and some of you took out your handy dandy calculator and you did 6 divided by 0. So take 6 divided by 0 on your calculator right now. I'm going to do that on my count. 6 divided by 0. And what do you get on the display of your calculator? Robert, what's the display of your calculator show you if you take 6 divided by 0? Does it show you 0?
No, I get math error.
Yeah, you get math error. Yeah. How about 0 divided by 6? What is it? Clear your calculator. If you take 0 and you divide by 6, do you get math error or do you get a 0?
0.
6 is a 0 divided by 6. Robert, what do you get?
Yeah, I get 0.
Yeah, just like here on the display of my calculator in the inset, you're going to get a 0. However, it's not 0 divided by 6, it's truly 6 divided by 0. So what is this thing, 6 divided by 0? What is this math error? The math error is you have to go think back to what you're doing to this battery. Okay, some of you drive a car, some of you are sitting and you're being chauffeured by your parents, but some of you drive a car, and those of you who drive a car, if you've ever looked under the hood, if mom and dad have ever opened up the hood and say, okay, here son, here daughter, take a look under the hood, this is a battery, don't put your hands on it. Okay, why? Because it'll shock you. So a better example is your 9-volt battery and the toys that you and your younger cousins have played with. 9-volt battery has 2 terminals, yes? Do you ever put a metal penny across those 2 terminals? Do you ever put any kind of a coin between the 2 terminals? No, because what you're creating is known as a short, and that's what you're doing with this piece of wire. So if I come back here and go back to the share, take a look at this for a moment. We're talking about our 9-volt battery, and it has a terminal here and has another terminal here, and has a plus and it has a minus. And you never, ever put anything metal across these 2 terminals. Now, some of you know this when you or your younger cousins have had a toy that works on a 9-volt battery, and that toy starts failing because you're thinking the battery has drained. What is the fastest way you can test this 9-volt battery? How many people have done the famous tongue test? No? Robert shakes his head. Vijay shakes. No? None of you have done the tongue test? Seriously? Brad, have you ever done the tongue test on a 9-volt battery? Oh my goodness. All right, well, that's probably because, probably because all the toys that you and your cousins have played with don't use 9-volt batteries. But if in fact they ever did use 9-volt batteries, the famous tongue test where you actually put the battery right up to your tongue, a little tingle between the terminals tells you, okay, a little tingle, it's a weak battery. And you take a fresh battery and you put it on your tongue, just momentarily, it'll give you a pretty good jolt and say, oh boy, that's a strong battery. Okay, I can use that in a toy. So, but conceptually, what's happening is when you're doing your tongue test, you're connecting these 2 terminals with a wet bridge. You're shorting these 2, and by shorting these 2, you create a very bad situation. You can, if you leave a penny or a coin, or if you put this in your pocket full of change, and some coin happens to come in contact with this thing will drain itself very quickly. It'll get very hot, and it can also cause a fire, okay? We don't ever want that to happen. So I made a recommendation on some of your comments on question 10. Those of you who looked at question 10, I made a comment that you really ought to go back to this PowerPoint. So let's go back to here. And let's go File. And I want week 2 lecture. And on week 2 lecture, I referenced slide number 20. Slide number 20. Okay, let me go ahead and share that screen with you right here. Okay, can everybody see short circuits? This is back in week 2, and what you, if you don't recall it, you should go back and take a peek at it because it's very important, very informative. And what it goes to show is this: it defines what is a short circuit. Some of you may have heard the expression short circuit, and some of you may recognize that short circuit is a condition you don't want. Okay, it's no bueno, absolutely no bueno. So what is this thing called a short circuit? It says it's a circuit where there is a low or 0 resistance wire called a short that is either accidentally or intentionally introduced to an electronic circuit or component. The short provides an unattended near zero resistance current path that can result in what? Excessive current flow that can what? Damage or destroy the electronic device. In the case of the battery, we have introduced a short circuit. That battery will blow up, or certainly heat up and may cause a fire. If you do that on mom and dad's car battery, you're probably not going to see Thanksgiving. They're going to be very upset with you because that battery will be destroyed. So do not short circuit your battery. So let's see what happens here. Take a look under normal circumstances. So I start this illustration with the normal circuit. With the normal circuit, 12 volts, 1 k ohm, 2 k ohm. There's only 2 resistors. There's a total of 3 k ohms. And 3 k ohms divided by 12 gives you 4 milliamps. Under normal conditions, what is the voltage across the first resistor? 4 volts. What is the voltage across the second resistor? 8 volts. Does the 4 plus the 8 add up to 12, yes or no? Does this 4 plus this 8 add up to 12? Brad? Yeah, it does, right? The 4 volts drop across the first resistor, because this is the meter on the first resistor, measures 4 volts. This is the meter on the second resistor, and it's twice as big, measures 8 volts. And if you add the 4 volts that's measured across here, plus the 8 volts measured across here, it should add up to be the total of 12 volts that is applied. And here's how the meter is set up to measure current. So when we come back to lab on Monday, we will be measuring current on your boards, okay? So this is under normal conditions. Now, if I take and introduce a wire, so I'm going to put a wire between here and here, okay? I'm going to put a wire between here and here. So take a look. That's what happens in this circuit. Now I put a wire between point A and point B. And you're driving the electron bus. The electrons leave which terminal of the battery, Jacqueline?
The negative.
The negative, so it comes downwards from the voltage source, everybody, is that right? And then as it comes downward, follow the yellow arrow. It comes down to this corner, turns right, and it goes inside the amp meter, through the amp meter, outside of the amp meter, then it hits point B. Now, you're driving this bus called current. You run into point B. Do you see that the current can split between a path going up and a path going to the right? There's 2 paths here, okay? And how much resistance is there in this path on this straight wire between point B and A, just coming straight up? How much resistance in an ideal piece of wire should be 0 ohms? No resistance on a piece of wire. That's why we use wires to connect our circuits. Take a look at the path going to the right. The path going to the right, current comes up here, current comes up here, and then all of a sudden it sees a resistor. Uh-oh, it sees 2 k ohms. How many ohms on this path going straight up? 0. How much current on this path coming around to the right? 2,000 ohms. If you're driving this bus called current, which path are you going to take? Are you going to take the easy path of 0 ohms, or are you going to split and take this hard path of 2,000 ohms? You're going to bypass the 2,000 ohms. You have no interest going down this path. You're going to come straight up. Current will take the path of least resistance, and there's 0 resistance on this wire. So what has happened in this case? The electricity will no longer flow through the 2 k ohm. The 2 k ohm resistor will have been, there's a word for it. What is that word? That 2 k ohm R2 has been bypassed. That electricity will ignore it. It will come straight up this wire from B to A, and then only flow through 1 resistor before it goes back to the 12 volt source. Now do the math. 12 volts. How many resistors do we have in the current path? 1 or 2? We have only 1. And how many ohms is this guy? 1K ohm. So do the math. What's my current now? My current is 12 volts divided by 1K ohm. 12 divided by 1,000 equals, and then hit engineering key. Does your calculator show you the current that I've shown here on my slide, 12 milliamps? Is that what you calculate? What was my current before? Under normal circumstances, my current was happy at 4 milliamps because I had 2 resistors in the current path. But now, because I put a short in here, my current, did it go up or did it go down? Benevetti's, did the current go up or did the current go down? Did the current increase or did the current decrease from the original to now? Robert.
Is it the same?
Well, here's the original. How much current was in the original? What do you see here?
Oh, it went up.
Yeah, so it's 4 milliamps here. And then once we introduced the short, it's now 12 milliamps. So the current went up, the current increased. Everybody see that? And so if the current increased, that's not good for us, because if we have an increase of current, our wire is going to get hot, our component's going to get hot, something might burn out. That's really not good if a short circuit happens. So read the captioning here. It says a short has been placed between points A and B. This short will cause the electron current to what? Bypass R2 with 0 amps flowing through R2. VR2 will be 0 volts. There's no current going up on this path right here. No current, no volts. This guy is basically now out of the picture electronically. There's only 1 resistor left in the current path, and that's all we have. And current increases. If I go to the next slide puts the jumper wire between point C and D. It wasn't there before. There's nothing on the left-hand side of the voltage source before. But now, let's say a paper clip or something unfortunate falls into the circuit, and a wire now connects points C and D. Is there continuity? Is there a complete path for electricity to flow? Yes or no? Yep, sure is. Is there any ohms in this current path? Yes or no? There's no ohms. What you have is a very special kind of short. It says here, a short has been placed between points C and D. This short will do what? It will bypass the entire circuit, okay? It's going to bypass the entire circuit. What does that mean? Take a look. The electricity previously, originally, didn't it come down and flow through this whole circuit? Once we put the short in, the electricity only flowed through 1 resistor, and we bypassed R2. Now by putting in the wire here, all the rest of this circuit has been bypassed. There's ohms here. Why should electricity flow where there's ohms when it has an opportunity to flow through 0 ohms? It will go do this. And what will happen is, because our total is now 0 ohms, there's 0 ohms on that piece of wire, current will briefly increase to what? Infinity. And the voltage source will be what? Damaged, or it could also be destroyed, okay? And that's what would happen in what we call a very special kind of short. What do we call this short? This is called a dead short. Why is it called the dead short? Because that voltage source will be dead within moments of us doing this. So we'll never do this in real life. This only happens in accidents, okay? But that's what question 10 goes to ask you. It asks you your thoughts about short circuits. So here's a normal circuit again. Here's a short circuit, meaning we put a wire somewhere in here and we bypass a component. A short circuit will increase current. And if that short happens to be across the terminals of the battery, you have a very special short known as a dead short. Everybody okay with those terms? Okay. So just because week 2 is behind us doesn't mean you should not go back to week 2 and take a look at these topics. We talked about series circuits. Well, then there's series aiding and series opposing voltage sources. How do you reconcile that? You should go back and look at your PowerPoints. They're very informative, okay? And then there's, in week 2, an introduction to the digital multimeters, a very brief introduction. And then there's circuit analysis, and we're measuring voltages. We do calculations and we measure voltages. And you happen to have a circuit that's very similar to this that you're going to be verifying, if you haven't already, the voltages across resistors, and then more circuit analysis and more. And especially here, this is very interesting. We have an exercise in Canvas, and in Canvas, we go to here, give it a moment, and come to, let it stabilize, find our, okay. And we have circuit, I want to get to, let's see which one here, circuit G point voltage and current analysis. So open this particular guide. Some of you have submitted this, some of you have not. And let's take a look at this in this format. Can you see this Word document? Raise your hands. Okay, all right. So, oops, wrong button. Silly me. Okay, here we go. All right, so circuit G, this is something that you all need to get done. Some of you have done this, but you all need to get this done if you haven't done this. You have calculations on one side with the switch in the open position. Here's the switch. And you have measurements on the other side. Now, the purpose of the LED, is only to allow you to see visually that the circuit's working. Some people did not remember this when they were doing measurements of circuit, circuit F. Some of you did not remember that I said, once the LED lights up, that means your circuit is built correctly. What you need to do is you have to pull the LED out and put a jumper wire back in here where the LED was removed. Otherwise, your voltage measurements are going to be wrong. All right. So, case in point, looks something like this. Case in point. If I happen to have the circuit here, and I'll get a power supply. Nice. So let's go ahead and switch from here into here. All right. And let's go ahead and power this fellow. Yep. Power does good. We like that. Yay. Nabil, you're a lifesaver. Oh my gosh. All right. Cool. So here's the circuit, and the circuit happens to have a number of components and has different points of measure, a point A up here, a point B, a point C, a point D, and then an LED. And when we turn things on, the LED lights to let us know that, yes, we have built the circuit correctly. Once we have determined we have built the circuit correctly, we say you must remove the LED and you must replace the LED with a jumper wire where the LED was in order to complete the circuit. Now your measurements will be correct. If you don't remove the LED when you start making your voltage measurements, the LED, because it's now part of the circuit, will drop a certain amount of voltage. This guy will drop between 1.3 to 1.6 volts, depending upon the color, depending upon the manufacturer, but it's typically going to drop between 1.3 to 1.6 volts. That's going to mess up your measured voltages. They will not compare to your calculations because all of this is supposed to total your 5 volts. And if all of a sudden this LED is left in the circuit and is dropping 1.6 volts, there's only 3.4 volts left between these resistors. You can't have that happen. So look at that. I've made a mention on some of your circuit measurements that you really need to, after you verify that the LED works, the circuit's built properly, pull the LED out, as I've just done, and replace that LED. Now you have to replace that LED with a jumper, otherwise you have an open circuit. So now I've replaced where the LED was with a jumper that now bridges between this resistor and this jumper going to the blue rail. Does everybody see what I've done with that you need to do or you need to redo for your measurements? And then now if we go to do our measurements of voltage, of current, anything, everything now will be correct. So that was another point I wanted to make for you. Now, something very interesting though, since this is set up with 5, let me go ahead and grab a meter and we'll show you some measurements that will help make sense for everybody. So let me go ahead and put this on, put the recording on pause. I'll be back in 15 seconds. Let me grab a meter and recording. Okay. All right, so we're going to take the little tip protectors off of our multimeter and let's go ahead and see what we have on this particular guy. Go ahead and set the voltages to here and let's confirm we happen to have 5 volts on across all of these resistors. So as you know, the red probe is always going to be placed towards the positive side of the circuit. So I'm going to stab right here. That's where my voltage is coming in on this rail, yes? In fact, let me move my meter over this side. There, okay. And I'm going to go put my red probe over to here. That's where my supply is supplying on the red line, my positive 5 volts. And the measurement for my negative rail is right here on the blue line. I'm going to touch right there. So do I have, oops, go to 20. Do I have something pretty close to 5? Hey, how about that? 5.06 volts on this particular power supply. That means if I go across the resistors from here to here, this should give me exactly the same, yes? 5 volts. And if I go to measure across each one, so the first resistor, in this particular case, I have 2.57. If I go to measure the second resistor, I put my red probe here because that's the more positive side of the resistor. Put my black probe here and measure something less than a volt. So should I leave this here or should I change my scale on my meter? What do you think I should do, Miss Tay?
You should change your scale.
Yeah, because I'm on the 20 volt scale right now, and the 20 volt scale, I'm at 0.78. I should change my scale from 20 volts to go to my 2 volt scale in order to capture another digit of resolution. So I'm going to go to here, since the measurement is going to be under 2 volts. Now I'll see if I can get more information. Come back here, measure, measure, measure. Hello? Is this not working for me? It's making me a liar? Did I break something in the interim? Go back to here. And then if I do this guy, okay, it's clearly making measurements. Clearly making measurements. I'm going to go to 2. Maybe I have a bad switch position. That could be 2. No, okay, must have my probe in the wrong place. So did we capture one extra digit of resolution by changing the scale to the 2-volt scale? Yes. And so that's what we should do. So what it is that we happen to have, my friends, is this. We happen to have for R1, let's measure that guy again. We'll record the value. This guy from here to here, it was overscale, so I have to go back to 20. So here was what, 2.57, something like that. Okay, seems to be holding. Yeah, 2.57 volts. So I will write that down here. VR1 is 2.57 volts. And then my VR2, we were able to see that this was a decimal value. So stabbing technique, and while I'm stabbing, I'm holding that with one hand like chopsticks, which I'm sure you all are very adept at doing. And yeah, if you like sushi, you can hold chopsticks in one hand. 0.776 volts, yes? So I can write that just for quick and easy, VR2, 0.776 volts, which we know is 776 millivolts. And we're looking for a VR3, which was 1 point something and change, yes? So let's go ahead and do this guy here and this guy here. Ooh, look at that. Holding steady, 1.707, I'll call that, okay? So 1.707 volts. So do these values make sense? Well, move those out of the way, get our calculator, and let's add these guys up, because if these guys are measured correctly, if the circuit's built correctly, shouldn't this number plus this number plus this number, shouldn't it add up to be something close to our 5.05 volts that we measured across the first set of terminals? Let's see what happens. So we're going to punch in 2.57 plus 0.776 plus 1.707 equals, wow, 5.053 volts. And what did we do? We measured 5.05 volts, okay? So this is a valid value, so is this, and so is this, because they add up to something very close to our measured 5.05 volts. Watch what happens if I forget to pull out that LED. I'm going to leave that LED back in the circuit. It's nice and pretty. Yay, Mom and Dad are so proud of you. You got a lit LED. Look, Mom, I've got an LED. Now watch me make the measurements. I'm supposed to have 2.57 volts across the first resistor. All right, Mom, check this out. All right, this is going to happen. Check this out, Mom. I'm going to hook up here. I'm going to hook up here. Where's my 2.5? Oh, no. Hey, Junior, how come you don't have 2.57? You're supposed to have 2.57. Are you measuring the right place? You look at that and say, yeah, that probe goes at point A, this probe goes at point B. That's the first resistor. It's supposed to be 2.57. But now I get this 1.245. What happened? Well, let's check the next one. So you go to check the next one, and the next one is supposed to be 700 something millivolts, and you're half of that and say, oh no, something happened there. And you look at the last one's supposed to be 1.07, and oh, what happened here? This is so much less. And the reason why it's so much less is because this guy is dropping voltage. Let's see how much this one actually drops. I said it'll drop between 1.3 to 1.6 something. This one is actually dropping more than that. Green LED is really sucking up a lot of voltage. 2.62 volts for this green LED. Wow, that's almost half the voltage right there. So does everybody understand why you need to remove the LED and put the jumper back in place, and life is good? Wherever I put my jumper. It's away from me now. All right. Any questions about that so far? Now, there is one other thing that I want to confirm with you all, and that is voltages measured with respect to ground, or voltages measured between points and voltages measured with respect to ground. So I'm going to put the jumper back in. So here's the jumper. All right. Now, suppose, so these are the values of voltages we're supposed to have. Suppose you were asked V, A to C. You're shown A to C. That means the red probe has got to go here. Here's the red probe is always on the first letter, and the black probe has to be on the second letter. So I'm holding probes in my hand right now. Holding probes in my hand right now. I've got the black probe, which is supposed to go to point C, right there. And the red probe is supposed to go to point A, which is right there. Now, I'm not going to touch this yet, but what do you think we should have between these two probes? Didn't we measure the voltage across the first resistor as 2.57 volts right up here? Didn't we measure the voltage across the second resistor as being 0.776 volts? So if I'm measuring from point A to C, doesn't it look like I'm measuring across these two values of voltages? What do you think we ought to do in order to predict how much my voltage is between A and C? Mr. Weiji, what do you think we should do?
It's gonna be 2.57 plus 0.776.
We should be adding these two, you're thinking? So let's do that on our calculators. Let's go ahead, take our calculators, and let's go ahead, clear, and let's add 2.57, 2.57. We're going to add that to 0.776. Everybody do that? Okay, we're going to add that 2.57, add to the 0.776, hit equals, because we have to have a target. So what's my target? My target should be a measured value close to this calculation. I'm hoping to see something close to 3.346 volts. Watch what happens when I go to make the measurement. Okay, put this back into the view. I'm going to put my red probe at point A. So red probe at point A. Move this over here. There's my calculation. Red probe at point A. Black probe at point C. Boom. Wow. We calculated 3.346. Where do we measure? 3.34. Is that pretty spot on? We're happy with that? Hope so. So that calculated, slide this back over, calculated to be 3.346 volts, and what we measured was 3.34 volts. Pretty good. Now I'll give you something else to think about. Now I'm going to ask you to do, how about a VDB? Voltage between D and B. That means what color probe goes on the first letter? The first letter will always get what color probe? Red. What color probe will go on the second letter? Black. Will go black. So on my schematic, on my circuit, that means I'm going to put the red probe at point D, which is here, and then I'm going to put my red probe at point B, which is here. I'm not going to touch this yet. What do you think we should have? Because we measured each of these before. Isn't this the voltage across the third resistor? Isn't this the voltage across the second resistor? And am I not putting the red probe at the bottom of this guy and then the black probe at the top of this guy? Is that what I'm doing? So what do you think my voltage ought to be, Mr. Robert Benavides? How do I determine what my voltage ought to be between these two resistors based on our previously calculated voltages?
You're going to add them?
Okay, we're going to add them. So what are we going to add? The 1.707 plus the 0.776? Let's go ahead and add them. let's clear 1.707. And I'm going to add that to 0.776. Boom. I get 2.483 volts calculated. Is that what you get also? Now, is it going to be 2.483 volts? That's what we calculate. Is that truly what it's going to be? Mr. Brad, what do you think?
It might be.
Might be, okay. Might, because the red probe is here, black probe is here. Jacqueline, what do you think?
Going to be negative.
It's going to be a negative, that value?
Yes. I think so.
How many people? Oh, okay, that's okay. So it might be this value, it might be the negative version of this value. Robert, what do you think?
I'm not too sure.
Okay, is it going to be this? Is it going to be something close to this value?
Well, yeah, it'll be.
Okay, there. And is it going to be positive or negative? That's the part you're not sure about?
I think it'll be positive then.
I think it'll be positive. Okay. To point D. Point D, isn't point D attached to the negative side of the voltage source? And the red probe is going to go to point B, which is up here. And isn't point B closer to the positive side of the source? Remember, when we were measuring with our red probe, black probe this way, we were able to get a positive 1.7. Yeah, this was a positive 1.78. What did we have here? Positive 1.706. Suppose I reverse the leads. I put the red probe down here and I put the black probe here. If I reverse, I'm sorry, you need to see this. I apologize. Let's go back again. If I put my black probe here originally, my red probe here originally on this one resistor, we expected something close to 1.707. And if I hold steady, am I locking in at 1.707? Yes? If I reverse these leads, if I put the red lead now on the bottom of the resistor and the black lead on the top, right there, is it still 1.707 or 1.70? Yeah, there's my 1.707. Do you see a negative symbol there in the voltmeter display? It clearly shows negative. Why does it show negative? Is because the red probe, remember the red probe senses polarity. When the red probe is pulled towards the black probe, this side of the resistor, the lower side of the resistor, is negative. Okay? If I switch the leads, put the red probe here on this side, it will be a positive 17.07 volts. My fingers are in the way. Positive 17.07 volts. But if I reverse the leads to go here and hold steady, it is a negative. So the voltage between D and B, we agree that it should be something like 2.483 volts, and we believe it should be a negative 2.483 volts. Let's see what happens. Red probe at D, black probe at B. Here's B. And I'm beyond scale because 2.483 cannot be measured on a 2-volt scale, right? So I'm going to do my handy dandy chopstick routine. One hand, change the scale with the other hand, and hold steady. And what does it show me? Negative 2.48 volts. Is that pretty close to our calculated value? And is it in fact negative because the red lead is at the bottom? Yay? So we have a calculated this, and we have a measured negative 2.48 volts. Negative, it equals to a negative 2.48 volts right there. How about if I switch the leads? How about if I do this? V, B to D. Where does my red probe go now? Always the first letter, right? So this gets red, the first letter, and then the second letter will get black. So now if I put my red probe at point B, so red probe at point B, now move this back into view, and my black probe at point D, so a black probe at point D, and move this back into view. It's still 2.48, but it is positive, yes? Whereas if I do it this way, it's still 2.48. Let me see if I can attack it here. Now I have to do it from this angle. I'm sorry, I don't want to be blocking the camera. So negative 2.48 if I have my red lead at the bottom of the stack. So this is, I wanted to review this with you because your task with this exercise, circuit G, is, let me go back to the share. This guy, go to share here and share here. Yeah, you're tasked with making measurements, making calculations first of voltages at 2 points. So for example, do I have a VBA? And where is VBA going to be measured? Well, B is here, A is here. Red probe on B, black probe on A. That's your VBA, okay? And that's when the switch is open. You're going to do a calculation for VBA when the switch is closed. So when the switch is open, will any electricity flow at all? None. Is there any current? None. If there's no current, then are there any voltages across these resistors? The resistors will have no voltage. Are we sure? If we break open the circuit, will the resistors have any voltages that we measure across them? Interesting question. So I'll tell you what. Let's go to our simple circuit again. Let's see if we can answer that question by doing this. Stop this share and go back here. I have a circuit that we know has been working. We've done measurements. I'm going to create an open circuit by removing this jumper. So if I remove this jumper, I now have an open circuit. Yes? Is there any electricity flowing once that jumper has been removed? Class? None. I have no continuity. I have no electricity flowing. If there's no electricity flowing, do I have any voltages across these resistors? In other words, am I going to be able to still measure 2.57 volts, 0.776 volts, and 1.707 volts across here if no electricity is connected? Well, let's see if I still have a voltage source. Here's my source, one here and one here. Is my source still good at 5 point some kind of volts? Yes, my source is still good. If I go to measure my first resistor was 2.57. What is my first resistor now with the switch open? Nada, nothing. What is my voltage across the second resistor? Was supposed to be 0.776. Measure across it, nothing. What is my voltage across the third resistor when my circuit is open because there's no electricity? Nothing. And why is it nothing? Because if you think about Ohm's law, V, I, and R, if I is equal to 0, I is equal to 0 amps, 0 milliamps, 0 amps. If there's no current, V is still going to be equal to I times R, right? Isn't V going to be equal to 0 times whatever my ohms are. Let's say it's 100 ohms. What's 0 times 100? 0 volts. So because we have no current, because the circuit is open, or in the case of the circuit G, because the switch is open, no current, mathematically the voltages here, voltage here, voltage here will calculate to be 0. But I'll show you something interesting. Suppose I measure across the open. Suppose I measure from here to here, okay? Because I had a jumper wire here. I had an LED there originally, and I had a jumper wire next. So we had an LED, had a jumper wire. We pulled this guy out. When we pull this guy out, what do we have between these 2 points? Actually, let me put the guy in. If I measure from here to here, to the blue rail, do I have any voltage whatsoever? Do I expect any voltage? It's a bare piece of wire. I don't expect voltage. There's no ohms here. I don't expect anything. And no voltage is measured as a result. If I pull this jumper wire up, what do you think we're going to measure between point D and the blue rail now? Question goes to Ms. Tay. What do you think? I'm measuring across an open.
I think you'll measure something.
I'll measure something, okay.
You'll measure something. I don't think it's going to be 0 though.
You don't think it's going to be 0, okay, because I no longer have a wire between the two. How much ohms do I have between the two? Lots. Got a whole lot of ohms. It's infinite ohms, okay. Food for thought. If you measure something, question goes to Robert. What do you think we're going to measure? Are we going to measure any kind of voltage at all if I put my red probe here, my black probe at point in the blue rail?
No.
I'm not going to measure anything. Brad, what do you think? Are we going to measure anything if I put my red probe here, my black probe at the blue rail?
I'm guessing it's gonna be more like, no, I don't. I was gonna say what you were talking about earlier about the infinite, but
Yeah, I have infinite ohms. And once I pulled that, because the wire, jumper wire was 0 ohms. Now that I've yanked it out, I now have infinite ohms here. I got a whole lot of ohms here. So am I going to measure any kind of voltage? Food for thought. Food for thought. Not sure. Mr. Wei Ji, what do you think?
I think it's gonna be 5 volts.
You think we're going to measure 5 volts? Positive or negative?
Positive.
Are you positive? Moment of truth. Red probe here and black probe here. And you can see my meter, yes? We measure all of the voltage here. Why do we measure all of the voltage here? Simple reason. Do I have a series circuit from the red rail through here, this yellow jumper, through these tie points to this orange jumper, across the jumper through these tie points to the first resistor, jumper, second resistor, jumper, third resistor, down to here? Once I'm here, am I completing the circuit with my meter probes? Okay, I have a series circuit and I'm measuring across an open. So what this comes down to, my friends, is this. Whatever the ohms are, we never really looked at the ohms on this guy. I have a voltage source. There's 5 volts. 5 volts. I have a resistor. I have a resistor. I have a resistor. And then now I have an open. And the open, we said, was infinite ohms. How many ohms on this guy? Let's go ahead and check. Let's go ahead, disconnect my power. And let's go ahead and measure the ohms. And so the first guy, 330 Second guy, 100. So I have 330 ohms, 100 ohms, and last guy probably 220. Yeah, close to 220. 220 ohms. And over here I happen to have infinite ohms. So if you go back and think about, do you remember this statement in series circuits? In series circuits, the largest ohmic value resistor will have the largest voltage. Do you remember something like that in our summary? It isn't phrased quite like that, but it's something like that. The smallest ohmic resistor will have the smallest voltage. Wasn't that the case when we did our measurements earlier? When we did our measurements earlier, and I put these two guys side by side here, watch this. This was our smallest ohms. Didn't it drop the smallest amount of voltage? This was our largest ohms. Didn't it drop the largest amount of voltage? This was our in-between ohms. Didn't it drop the in-between amount of voltage? So do we have proportional distribution? Bigger ohms, bigger voltage, yes? Smaller ohms, smaller voltage, right? And we're going to use that same principle right here. Largest ohms will have the largest voltage. Well, guess what? That's only 330. This is 100. This is 220. This is infinity. This is way, 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 way bigger than all of those combined. So where is all the voltage going to be? There's going to be almost nothing here, nothing here, nothing here, but all of it will be here. And that's why we measure 5 volts on that open. Interesting. So let's go ahead and put that open back in. I'm going to put that short back in. Boop. Now the short is back in, and I'm going to turn the circuit back on. Now the short is back in. I'm going to go to measure back to voltage. And let's see if I still get my 0.77 something. Yeah, there's my 0.77, and here is my 1 point something. Yeah, 1.707 volt. Sorry, you can't see that. I apologize. Right here, we still have my 770 something millivolts. And then right here, I still have this, yes? Now, I'm going to remove a different jumper. Yank a totally different jumper. I'm going to yank this jumper right here out of point B. If I can grab it. Got no fingernails. This is challenging. Okay, I've yanked the jumper out of point C. Do I have an open in this series circuit? Do I have any electricity flowing in this circuit right now? The answer is no. If I have no current, do I have any voltage across the resistors? No current. Do I have any voltage across R3, across R2, or R1? Brad, what do you think? No current because I pulled that jumper out. Will there be any voltage across the third resistor, yes or no? None. Let's check. Boop. We get 0. How about the voltage across the second resistor? Robert, should I have any voltage across the second resistor, yes or no?
From where?
Well, right here, across the second resistor. I'm not touching it yet, but I will in a moment. How much voltage will I have across the 100 ohm resistor when the circuit is broken open? Will I still measure my 0.776 volts? Yes or no?
No.
And no. And then if we do the same for the first resistor, we have a no. How about if I put my probes here on the open, if I put my probe here at the bottom of R2 and my probe at the top of R3, because here's the open, I've removed the short. What do you think I'm going to measure between these two resistors where the circuit is open? Jacqueline?
5.61.
5 point something, yes. Let's hook this guy up here. And let's hook this guy up here. Oops, exceeded the scale. Change the scale. Wow. Do I measure my source voltage here? Why is all my voltage here? Because I have infinite ohms on the open. That's only 330, that's only 100, that's only 220. Between these two probes, I have infinity, and that's where all the voltage will be measured, okay? All right, I'm gonna put these guys back, all right? So I think this will help give you a little more background on what it is that you need to help you understand what's going on with this particular circuit, which you all have and that you all should be building. So let me change the share to here, back to here, to there. Okay, so that's for this particular exercise right here. And so, like I say, Jacqueline, in the somehow in the word processing, those last rows are gone. So please look at your document again and reformat it to recover it so I can see what those values are, okay?
I will.
Thank you. All right. We talked about the graph, we talked about shorts, talked about the homework review questions. Okay, we want to talk about conductance. So, topic is on conductance. Conductance. And conductance is defined as the ease of flow of electricity. The ease of flow of electricity. Conductance equals the opposite of resistance. In fact, conductance symbol is capital G. And the units are one of two. One of them happens to be called MHOS, mhos. And the symbol for mhos is the upside down omega. The other unit, the European unit, is called Siemens, S-I-E-M-E-N-S. And the symbol for Siemens is a capital S, not a lowercase s. A lowercase s stands for seconds, but a capital S stands for Siemens. And there's one other interesting thing. We said that conductance is the opposite of resistance. Conductance symbol is G. G can be shown this way, is equal to 1 over R, or R is equal to 1 over G, okay? They are reciprocal quantities of each other. So where this becomes significant is this. If I were to show you a parallel circuit right here and right here, and let's do a third one, what the heck? All right, let's do 3 resistors. Right here, right here. And let's say this one's R1 and that's 100 ohms. Let's say this is R2 and that's 200 ohms. Let's say this is R3 and this is 300 ohms. And current is going to come into the circuit right here. So we have current. It's going to come in and it's going to go down here. Some of it's going to split to come down. Some of it will continue. As it continues, some of it will split to go down and some of it will continue. So the current that flows into this bank, remember that the nickname for parallel circuits is called the bank, the current splits. So we have a split right here, we have a split right here. And then the current that flows through R3 will come here. And to this node, the current that flows through R2 will come down. So what happens at this bottom node is they combine. And then this now flows here. And guess what? With the current that comes down through R1 and the current that comes from these two, what happens at this node is that they combine. And then the current goes back to wherever it came from. So the current paths are shown this way through a parallel circuit. Now, if you were asked to calculate, what do you think, which path would represent the highest ohms? Well, the highest ohms, 300 ohms. This is the least amount of ohms. And if you think about resistance, isn't resistance, remember the drawing that we had for resistance? Wasn't the drawing for resistance like this? You had a pipe and then it narrowed, kind of like that. Remember that drawing? And there was a lasso that was fastened around there. So we say that the narrower we make that pipe, the more resistance we have. The narrower we make that pipe, the less current can flow through. Does that make sense? So which one of these should have the most current? Which one of these should flow the highest amount of electricity based on what we've said so far? What do you think should happen with this? Robert, what do you think? Document. It actually turns out to be the other way around. And this is part of why we need to have this discussion. The more resistance, the tighter we make this, okay? The more resistance, the tighter we make this. The tighter we make this, aren't we constricting the amount of electricity that can flow through? So if the ohms are high, the current is going to be equal to the least. These ohms are low, so the I is the highest here. So highest current where you have low ohms, least amount of current where you have high ohms. Can we calculate what the conductance is going to be? Go ahead with your calculators and calculate for conductance. So we said that G was equal to the reciprocal of R. So let's go ahead and do that. Take our calculator, turn it on, take 100. And how do I calculate reciprocal? Well, remember, you have a x negative 1 key, right? All you have to do is key in 100 right now. Take your calculator, key in 100, and hit the x negative 1, boom, and then hit equals, and then hit engineering. And what do we have here? According to my calculator, this is 10 something. What am I reading here, Mr. Weiji?
10 to the negative 3 power.
Yeah, 10 to the negative 3. And 10 to the negative 3, Yusef.
It's milli, 10 milli.
Yes, excellent, Brad. Yeah, Yusef he's there somewhere, but he's not with us. Okay, so it's 10 milli. And what are the units? What are the units of conductance? We can say Mohs or Siemens. Let's just go ahead and use Siemens. So what it is that you've calculated right here, this 100 reciprocal, this works out to be 10 milli Siemens. Using the same method, calculate the conductance for 200 ohms. So what you do, everybody, you clear your calculator and you type in 200 and you hit your reciprocal key right there. You hit the equal key right there. And then you hit your engineering key right there. And what do we have? Your calculation here, Robert, what do you calculate?
I got 5 millisiemens.
Precisely. You have 5 millisiemens, okay? And then for the last one here, Ms. Tay, take 300, so everybody will do this together. So 300, hit reciprocal, and then hit the equal key. And Ms. Tay, what do you calculate? And after you hit engineering.
How much is this
Jacqueline?
here?
Oh, okay, she dropped. All right. Mr. Wei Ji?
3.33 millisiemens.
Okay, so 3.33 millisiemens. All right, so how did we define conductance? Conductance was defined as the what? The ease of the flow of electricity. Which one of these has the easiest flow of electricity according to what we've written here so far? Which one of these has the highest conductance? Is the first branch. Lowest ohms, highest conductance. Highest ohms, lowest conductance of 3.33 millisiemens. Okay, so remember, conductance is the opposite of resistance, and they're calculated as reciprocal quantities. All right, okay. And that's what I have for you all for now. This session will be recorded and will be transcribed for you, and you should see it. I should be able to process it and put it on YouTube, hopefully sometime in the next 24 hours. And so you have your game plan between now and Monday, yes? So get everything in by, look at your grades, look and see where the zeros are. You can make up the zeros, because I said my middle name is flexible up through this week. You've had the extra week, because this is still officially week 3. We're not in week 4 yet. Week 4 begins next week. So you've had an extra amount of time to get things done. Don't procrastinate. Look at where the zeros are. Get those things done. If there's any questions that arise, go ahead and throw questions on Discord, and some of your classmates who see those questions will likely want to answer them. And if nobody does, then I will answer them. So that's what we use Discord for. Okay, my friends? All right, so that being said, I thank you all very much. Let's go back to here, take this off of here, and back onto the front camera. Yay. All right, so with that, have a great evening. We will see you on Monday in class, yes? Good job, everybody. Take care.
Mr.
Bye-bye.
Cole, I actually had a question real quick before I leave.
Yes, please, Robert, yes.
Everyone else can leave, it doesn't matter. But so for the conductance, the symbol,
Yes.
like, didn't we have a chart with the units and stuff like that?
Yes.
Okay, I was just making sure.
Yeah,
Was
conductance
it in
is
the
on
week
that,
1
is
lecture
on
or
that
the
chart.
week 2? The
Oh,
like the
it's-
chart.
it's-
I forget, because I was
it's
looking at.
probably, yeah, the chart should have been in week 1 or week 2, but it's in there, but it's definitely in there.
All right.
And you were definitely shown Mohs with the upside down omega symbol, and you were also shown Siemens with a capital S.
Okay.
Okay? All right,
Thank
good
you.
question, my friend. All right, you're very welcome. Have a lovely day. We'll see you, and Weiji, we'll see you when you drive safely. Take care. Bye-bye.